Greetings, boys and girls. In this video, we are going to look at the 2018 Physics 1 AP exam question number 3, which is a 12-point question, and it is a qualitative-quantitative translation question. So that's one of the two questions you're guaranteed to have on the 2020 online AP exam. So these are kind of things you want to be focusing on. There's a lot of graphing going on in this. So at the end of this video, let's talk briefly about how graphing might look different for you on an AP exam that's supposed to be done online with a keyboard. So let's get into this thing. We have this disk, which is spinning about an axle at its center. So this could be like a bicycle wheel or something like this. The student does some experiments and reveals that while the disk is spinning, friction between the axle and the disk create a constant torque on the disk. So constant torque is kind of something important to realize because that tells you that the acceleration of this thing is going to be constant. That's going to have some important impacts on the graphs below. Speaking of graphs below, we are supposed to create graphs of the disk's angular velocity as a function of time and as the disk's angular acceleration as a function of time. So I would start with the acceleration. That's the simpler one to do because I know the torque is constant, therefore I know the acceleration is constant. So we're just going to draw some constant non-zero value, and that's actually going to get us 1 point just by doing that. And then the second point is if we have a negative angular acceleration. Well, how do you know it's negative? Let's see. It's spinning counterclockwise, which is positive. They even tell you counterclockwise is positive. That is something you're expected to know. And friction would be slowing it down. And so the torque due to friction would be slowing it down. So if it's spinning the positive direction of slowing down, the acceleration must be negative. And so that's how I know that this acceleration should be negative. So constant negative acceleration will get us 2 points. The angular velocity graph, well, we're told that it starts with initial angular velocity omega naught. And so it's positive because it's rotating in the positive direction initially. So omega naught would be my starting point. And then it's going to go from omega naught to 0 because it tells us that at time t1, the disk comes to rest. So we need to get down to 0 by the time we get to time t1. So start at omega naught and then a straight line going to 0. How do I know that it's straight? Because the acceleration is constant. So remember that this graph over here is the slope of this graph right here. So if this graph has a value of -2, just for example, then this slope would be -2 as well. And so that's how I know that this has a constant slope because this has a constant value. So the scoring on this, if we have a velocity that starts at positive omega naught and goes to 0 at time t equals t1, so it's got to start here and it's got to end here. That gets you the first point. And then the second line is that you draw a straight line going towards 0. So if you drew something like this, that would be a straight line with the velocity approaching 0. So that would get you the second point, but not the first. If you do something like this, that's supposed to be a curve. If you drew a curve, you get the first point, but not the second point. The first point is basically starting and ending at the correct spots. The second point is for the correct shape. All right, so those are the graphs. We're then told that the magnitude of the frictional force exerted on the disk is tau naught. We're supposed to derive an equation for I, the moment of inertia, of the disk in terms of tau naught, omega naught, T1, and fundamental constants as appropriate. So 1 point, if we use some application of Newton's second law for rotation. So net torque equals I alpha, or alpha equals net torque over I. Anything using Newton's second law for rotation would get us the first point. We don't have the acceleration, but we do have the change in velocity, and we have a change in time. So we can just use alpha equals change in omega over t to get our alpha. So we're going to end at 0 velocity. We're going to start at 0 time. So this ends up just being negative omega naught over T1. So then I could just substitute that in to my Newton's second law equation like that to get the correct equation in terms of the givens once I solve it for I. If you have a negative sign in there or not, no big deal because the question just asks you about the magnitude of the frictional force. So if you have a negative sign in there, cool. If not, even better. Okay. So kind of recapping that, first thing we're looking for is a correct application of Newton's second law, correct application of some appropriate kinematics equation. Everyone can't think of anything you would do other than alpha equals delta omega over delta t. And then if you got the whole thing derived correctly, looks something like that, then you get the third point. Getting better with the mouse thing. Okay. And again, doesn't matter if you have a negative sign in there or not. Question asks you about the magnitude. Okay, so that is part B. Now we flip the page, and now we have to realize that something's going to change because we're told in another experiment. So part of the challenge with these things is just keeping straight what's changing and what's not changing. So what's not changing is the initial velocity starting at time t equals 0. And then at time t equals 1/2 t1, so that's going to be like halfway from 0 to the end of the graph. The student starts stripping oil on the contact surface between the axle and the disc to reduce friction. Okay, we don't have to worry about that until 1/2 T1. So he's going to start reducing friction, and so the net torque is going to go down as he drips more and more oil onto the surface and reduces the friction more and more. Okay, so keep in mind that that doesn't start happening until 1/2 T. So really, for the first part of our graphs, we should just copy what we have from part A. We should still start at omega naught, and we should still slope as if we're going to go to t, 0 by the time we get to t1. Over here, we should just draw a flat line wherever we had it before. Okay, so nothing's different about this situation compared to the first situation until we get to time 1/2 t1. Okay. So at time 1/2 T1, that's when the student first starts to drip oil on the contact surface to reduce the friction. So again, in thinking about what's going to be different, I would start over here with the acceleration graph. If we're decreasing the torque, we're going to decrease the acceleration. So now instead of having a constant acceleration, the acceleration is going to start to get smaller. And so that's why this is going to trend towards 0. If it reaches 0, okay, but it probably won't. It's probably not going to drip oil on this thing while it's spinning and totally take away friction. What you should not do is have this thing go to 0 and then like the acceleration all of a sudden start, like you make it so oily it starts to speed it up. That doesn't make any physical sense. So it should go towards 0 but not reach 0. So scoring on that is 1 point decreasing the magnitude of the acceleration between 1/2 T1 and T1. And so showing that, all right, I went from a flat line to a smaller acceleration after 1/2 T1 gets you the first point there. If you have your alpha go to 0, that's cool. It's just going to stay at 0. You can't cross the horizontal axis there because then you're somehow speeding it up by taking away friction. That doesn't make any sense. Okay. Over on my velocity graph, first point is going to be for a clear change of slope at 1/2 T1 with a decrease in omega after that. And so what that means is that this needs to start flattening out. And so we draw our slope like this as the change in change in omega gets smaller, it's going to start to flatten out. So in other words, if you got the acceleration all the way down to 0, it should be a constant velocity after that point. So that's why this is going to be a curve, and it's going to, that's not very good. It's going to kind of flatten out. So ideally, if your line goes to 0 over here, like that, this would be a flat line. Okay. So let's look at what the actual scoring says. 1 point for a clear change of slope at 1/2 T1, showing a decrease in omega after that. So showing it going down and flattening out would be that first point. 1 point showing a decreasing rate after 1/2 T1. So that's any kind of curve that shows omega getting smaller. And then 1 point for not reaching zero at or before time T1. So where do we get that from? Well, before it stopped at time T1, if we take away friction, it's going to still be spinning at time T1. So if your graph does not reach zero at or before time T1, then you get 1 point. So I kind of interpret that as meaning is you just draw whatever random thing, as long as it never goes to zero, you would get that third point. So it's a total of 3 points for the graph of angular velocity versus time, 1 point for the graph of angular acceleration versus time. All right, and then part D, this looks kind of scary, but it's really not. A student's trying to mathematically model the magnitude tau of the torque exerted by the angle on the disk when the oil is present at time t greater than 1/2 T1. So what this is telling you is this is for after we started dripping the oil on the axle. A student writes down the following two equations, each of which includes a positive constant, C1 or C2, with appropriate units. What's the deal with a positive constant with appropriate units? That's so that you can't just use dimensional analysis to figure out the unit for the answer and figure out which equation is correct for that. And so that's to say, all the other stuff in the equations is all kind of bundled up in C1. What we care about is can you interpret the time aspect of this thing. So don't worry a whole lot about what those are doing. They're just there to kind of fill in the rest of the units and everything that would be in the equation. So this is like, okay, what's going to be true is the torque dependent on the time minus the time that it started, or the time plus the time that it started, but the inverse of that. So which equation best models this experiment? We have to check equation 2. If we don't check equation 2, we can't get a point. And then we have to explain that as a reasonable explanation connecting time. So those equations are all about time and torque. So if you look at equation 2, as t gets bigger, like t being the variable t, as we go along the x-axis, 1 over something getting bigger would indicate it getting smaller. So in this equation, as that gets bigger, 1 over that would get smaller. And so that shows as t gets bigger, tau gets smaller. The top equation, as t gets bigger, tau will get bigger. And so that's saying as time goes on, and the student drips more oil into the contact between the two surfaces, that the torque is getting larger. So that doesn't accurately model what's happening. The torque is actually getting smaller as he drips oil into that. The second equation does show correctly increasing t decreases tau. And so we just have to have a reasonable explanation of that. If we check equation 1 over here, then we can't earn any points. So this is another one of those questions where it's just, does the equation have the correct functional dependence between this variable and this variable? That's all that kind of question is really asking you. Does any of this stuff over here matter? It's just there to cover everybody's bases to make sure that you're focusing on the time after you started dripping the oil instead of before we started dripping the oil. So don't let that confuse you. What's 1/2 T1? That's a number. So if you just want to replace that with a number like 3, okay. So that's just a number. So really it's just about the variable t. How does the variable t affect the variable tau? At the end of this question, that is the end of this question. Okay. So kind of rehashing real quick. First, we were asked to interpret this relatively simple situation of a constant torque. We were asked to graph it. We were asked to derive an equation to get the rotational inertia from it. Then we made it real tricky, and we changed something. And we actually changed it in a tricky way. so that something was decreasing over time. So we very rarely in physics 1 see forces and torques changing over time. So that's what makes this part really difficult. And so if we start with the acceleration graph and go, all right, it was a constant acceleration. Now the acceleration is getting smaller, and then work backwards to this graph, then that kind of be a best approach for it. And then this looks real scary, but it's real simple. It's which equation shows how t corresponds to tau. And so those are all very typical examples of what qualitative quantitative translation questions mean on the AP Physics 1 exam. Now, it is currently 2020, and we're learning from home, and we're going to be doing our AP exams online this year. And we've been promised that you should be able to answer all these questions with a keyboard. So, how could I possibly have a question like this that could then be answered with a keyboard using symbols? Well, it's really easy. Instead of saying, hey, student, draw these graphs, I could go, hey, student, here are two examples of a graph. You tell me what is right and what's wrong about those two graphs. So, for instance, I may have an angular velocity graph that does this and say, hey, what is wrong with this? What is right about it? Well, it's right that it's got a constantly decreasing um, angular velocity. It's wrong in that it doesn't reach zero at the correct time. Or maybe I gave you something like this. Say, all right, what's wrong with that? Well, it starts and stops at the right values, but at the wrong direction. So negative omega will correspond to the opposite direction. So those are the kind of things they can ask you with that. I could do something similar here. I could say, what's the equation that you would use? You could type this out easy enough. Maybe not using Greek symbols, but you could probably use words. You could type out torque instead of tau if you had to. Or I could kind of play the same game where I say, here's a student's work. In which step does he make a mistake and explain what that mistake is? Same kind of thing with these graphs. What's the mistake? And then this is very, very easy to do with the keyboard because instead of deriving the equation, you're explaining why it's correct. And so if you look through these qualitative quantitative translation questions, there's a lot of these briefly explained kind of things. Those could be the kind of things, or definitely the kind of things you're going to see on your AP exam. Okay, so if you have questions about you scoring yours, please email me or shoot me a comment in Google Classroom. And I hope to see you soon. Till then, ta-ta.